An alum of this institution from the physics department as an undergrad, and then went on and did a PhD in physics at the University of Rochester. Among the students, he's known as a mean drunk, and among his faculty colleagues, they refer to him as, quote, lucky to have a job. The next speaker, of course, is I. So I'm Scott Carney, and I'm here ostensibly to talk about inverse problems, but I'm really going to give this talk, which is about inverse problems, but it has the slightly sexier title, How Physics and Modern Computers Have Revolutionized Imaging. In some sense, the talk will have a metastructure to it. I want to tell a few stories, and I will tell essentially 3 stories about imaging from other people's work. And then 2 very quick little stories about my own that are relevant to biophotonics today in the modern context. All the stories I will tell have a certain cyclic structure to them. The idea that I'd like to get across is that advances in imaging generally have begun with discovery of some basic physical phenomenon. You must have some new physics to develop new imaging. Then analysis. That analysis includes theoretical insights into the physical processes, but also the mathematical analysis of what your data mean and how they are connected to the underlying objects. And finally, innovation based on the insight gained from the analysis, that the analysis should reveal new opportunities to glean information from existing data. And that's the real story of inverse problems. Inverse problems in the context of imaging are generally the practice of extracting from the measurements you can make in the laboratory the information you really wanted, or that the insights you really hoped to gain. So I'd like to, at the beginning, in case I run long here, just acknowledge a few key people. There are many people involved in this work who will not be acknowledged, but certainly my own postdocs, Bryn Davis and Sasha Khaviadanov, my former grad student Jin Sun, who did a lot of work on the near-field problem, and Yang Zhu, who's currently working on some of the work in ISAM, which I'll talk about. My close friend and collaborator, Steve Beaupart, who is my collaborator on OCT-type problems. Dan Marks, Tyler Ralston, and then again on the near-field stuff, Schottland, Markle, Bolgevoni, and Hillenbrand, all certainly Bolgevoni and Hillenbrand both are sort of the experimental guys who provide the data that make it all worth doing. Steve's going to play a big part in this, and I think some of his students are even here today. I don't know if Fred is still around, but if Fred is in the audience, Fred, you're here? Fred's gone. That's okay. And that's an ongoing piece of work. So I'd like to begin here, which may seem a little bit of an odd place to start. I mentioned earlier I calibrated this talk really for undergraduates, and so there is math left in. I think it's important to leave the math in. On the other hand, I think it's important to have the right frame of mind when looking at math, and so this is where I'd like to begin. Does anyone know what this is, broadly speaking? Anyone in the audience know what this is? Yeah, that's not the, what is it? Yes, it's a poem, yeah. It sounds like maybe you can actually read it. No? Okay, I can. But it's a poem. How do you know it's a poem? It has structure, exactly. So it has structure. So that's a lot of information already. And you should view mathematics like this. Math has structure. You look at it and you say, well, it's math about something. I can see that it has structure. Beyond it having structure, if I tell you just a little bit. First of all, it's Russian. Yes? Yeah. Okay. So next, I'll tell you that the rough translation is that this is a poem about snow blowing around the room in the winter and a candle burning on the table, and eventually the candle burns out. Written by a Russian. It's a death allegory. You know that immediately, right? It's Russian, it's about candles burning out, it must be a death allegory. So you've gained a lot of information. Not being able to read Russian, many of you probably cannot transliterate the Cyrillic. You don't need to. You just need to look at the structure, and you need me to tell you a couple of key things to understand it. And it's Pasternak, so it's gorgeous, it's beautiful, it's wonderful, and if you have the time, you can learn how to read it. but if not, you can just take my word for it. And that's how you should approach the math in this talk. This is a talk on inverse problems. So I'd generally like to introduce you to what inverse problems can do. Here we have three sort of fundamental technologies that have been mentioned already, I think, in various contexts and will be mentioned again in this summer school. First is radar. Next is nuclear magnetic resonance spectroscopy. Next is X-ray projections. All three of these technologies arose due to fundamental discoveries in physics and the direct use of those discoveries to make images. Lastly, up here is something called optical coherence tomography, which I will talk about in greater detail later. So if you solve the inverse problem and apply the results of that inverse problem to the basic technologies that I just had up there, NMR becomes MRI. That is, the physics of spin flipping can be turned into an imaging technique in 3D. Radar can be turned into something that no longer requires a highly trained specialist to sit in front of one of those little scopes spinning around and going bloop. It turns radar into something that makes beautiful images. This is obviously an airfield with some hangars on it. If it was bigger, you'd probably be able to tell that yourself with no special training. And of course, X-rays become CT, computed tomography, which offer 3D rendering of the body rather than wondering what thing sits in front of what other thing. You can just sort of spin it around and get a better view. And part of the subject of this talk will be what happens to OCT when you apply solutions of the inverse problem. So, all right. So let's talk first about X-rays. So I mentioned this sort of triangle of this cycle that happens in imaging of discovery, analysis, and innovation. So over here, the discovery is in the physics, right? That the physics that goes into X-rays really, of course, like most physics you deal with, are Maxwell's equations, but a very special asymptotic limit of Maxwell's equations gives you asymmetrical optics, and then something called Beer's law, which I'll explain in just a second. If you write that down in equation form, remember, just look at the structure. Beer's law just tells us that the intensity of light that comes out one side of the patient is equal to the intensity that went in on the other side times some exponentially decaying factor. And that exponentially decaying factor depends on all this stuff in between, characterized by an absorption index. The absorption index, alpha, is a function of space, and it's really alpha that we're after. So we can measure this, but we want to know this. And getting from these intensities to this structure is the subject of solving the inverse problem. The basic discovery, to give it a little historical context, most of you will know, goes back to Röntgen. So Röntgen is a pretty amazing guy. Here it is, 1895, makes this first image of his wife's hand. This is a ring and the bones of her hand. Imagine having never seen anything like this before. It was astonishing. Röntgen won the Nobel Prize in Physics. And when he won the Nobel Prize in Physics, it was the Nobel Prize in Physics. It was the first one, awarded to him in 1905. He's got units named after him, the Röntgen. He's known widely as father of diagnostic radiology. He's got institutes around the world, the Röntgen Institute. In many languages other than in English, X-rays are referred to as Röntgen rays. He was using a cathode ray tube developed by a guy named Philippe Léonard. Léonard was a Hungarian. He also won the Nobel Prize a couple of years after Röntgen. Building the instrument matters. And so it's more than just a matter of going out and making the discovery. Actually building the stuff matters. It's a funny thing, though, because no one talks about Léonard rays. No one has named an institute after this guy. And this could have something to do with the fact that he turned out to be a Nazi. So, literally a Nazi. So this is, I think, a good life lesson embedded in the talk. If you're going to make great scientific discoveries, you must also simultaneously be a somewhat decent human being if you'd like anyone to take notice. So, all right. So here's how it works. Kent talked earlier about sort of the physics of electron-photon interactions. X-rays provide a particularly easy to deal with example of electron-photon interactions because the energies are so wildly mismatched that there's none of this funny sort of quantum mechanical, oh, it jumps up and down a couple of energy levels kind of things. The binding energy typically in most atoms for the outer electrons is something on the order of 1 to tens of electron volts. X-rays that are used for this type of imaging come in with hundreds to hundreds of thousands of electron volts. So a photon comes in, it finds itself a poor innocent stray electron and pow, knocks it loose and ionizes the daylights out of it. That photon goes away, the electron remains with all this excess energy and goes about to wreak havoc in the living thing that you've just turned it loose in. And this is why X-rays are referred to as ionizing radiation and present a mild danger to the patient in low dosage. So, oh yeah, and I learned how to do animation stuff, so I was so happy with myself. That's an electron being ionized. Okay, so it turns out that this process happens most easily when the electrons are sort of loosely bound in the outer shells. Those sorts of things are generally known as metals, and a few key metals that act as excellent absorbers are things like calcium, magnesium, barium, and calcium's in your bones. So it turns out that you cast a pretty good shadow, or at least your bones cast a pretty good shadow because of all the calcium in them. Magnesium and barium are used as contrast agents, so it turns out your intestines do not present terrifically great X-ray contrast, but when you fill those intestines with barium or calcium or barium or magnesium, they light up, and so typical medical diagnostic here introduces a so-called contrast agent to provide imaging contrast where there was none before. And of course, sometimes the deposit of metals is itself pathological. And so one of the key features that's looked for in mammography, trying to diagnose breast cancer, is the accumulation of what are called calcium deposits or calcifications. And that calcium shows up very bright and clearly in an X-ray. So here's how it works. I mentioned Beer's law earlier is the stuff of X-rays. It's the physics behind X-rays. So first you start out with rays. So I'm really making a big leap from Maxwell's equations over to a particular form of the solution of Maxwell's equations that give you ray optics. So X-rays come in as rays. Here I've got, 16 X-rays, photons if you will, that come in and encounter a slab of something that absorbs X-rays. If that slab has enough absorption to, say, absorb half of the X-rays, half of the energy, then what comes out will be 8 X-rays, or in other words, 1/2. If you do that, take that slab and put it next to the first one and do the experiment again, you'll have a half, and now you don't lose the rest of them, you lose half of the half, right? And then you do it again, you don't lose all of them, you lose half of the half of the half, and then you lose half of the half of the half of the half. And you see that if you quadruple the length here, then instead of losing half of your X-rays, you lose 1/16. And in general, this results in an intensity law that says I is equal to I naught times 2 to the minus alpha L, where alpha is some characteristic inverse length scale, and L is the actual length of the stuff that you're propagating through. So this is Beer's law in a nutshell. If I scoot back here really quick, this is just a fancier version integrating up over things that actually provide non-trivial three-dimensional structure of this, which actually is something that my 11-year-old can follow. So it's not that scary. Beer's law is incredibly useful. The inverse problem is pretty straightforward. So if you imagine I have data here that is represented by S, and I have some physics here that acts on the absorption index alpha. X-ray projections take, let's say here in a model object, if I take 2 projected views, say I come in with X-rays this way and make measurements on this plane, and my object consists of these 2 squarish little boxes with high absorption in them. On this plane, I'll see a single square, right? Because they line up next to each other, and that's the problem with X-rays. They're not really images, they're shadows. And the shadow of 2 things standing quite near each other tends to look like one shadow. But if I come in from a different direction, then I get a different projection, a different perspective, and I see the two boxes here. I'd like to, I've obviously chosen this example with a high degree of symmetry that lines up between the object and the projections that I'm taking. So it's a little artificial, more than a little artificial. If I just take the data that I have and invert it. So what does that mean? Well, physically, if you kind of think about the intuition here, I took everything and pushed it forward into this plane. So inverting it might mean taking what was piled up over here and smearing it back out this way. Okay? And I took everything with these rays and pushed it over this way and made two piles of stuff over here. Inverting it might mean just pushing it back out that way. If you do that, you get a very rough version of something known as back projection. Back projection, okay? And you look at this and you say, well, okay, so there's a little bit of stuff smeared out over here and there's a little bit of stuff smeared out over here where it shouldn't be, but where they lay on top of each other, they reinforce. And in fact, if I did that with, say, a whole bunch of other views, every time I added a new view, the right stuff would tend to be reinforced much more strongly than the wrong stuff. And this is how back projection works. It's a very intuitive idea. And in fact, we can think of that roughly as, well, alpha is equal to some inverse operator, the back projector, P inverse, acting on the data that I have, and I make reconstructions like that. So it turns out to work terrifically well, and of course, probably most of you are well familiar with this, but you know, you get all kinds of beautiful images now, and one of the nice things is the soft tissue stuff shows up much better in CT than it does in a simple projection, a simple shadowgram. The modern version requires many, 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 many views, something that Luke, sitting in the audience, can hopefully, if I have tough questions about this, I'm going to blame Luke and ask him to answer them. He's a student of Yoram Bressler here on campus, and Yoram makes his living making this technology much, much better. There's another little object lesson embedded in the history of CT, and that is that the original mathematical formulation of the problem and solution of the inverse problem was done by a guy named Johann Radon in 1917. In 1917, we had X-rays, right? I mean, 1895, Röntgen, his wife, come here, let me take a picture of your hand. But in 1917, really no one had dreamed about the modern computer. I mean, people had talked about Babbage machines and things like that, but no one had thought, I have an idea. I will take megabytes or gigabytes of data, or petabytes of data these days, as I am now approaching, and I'll get a machine to keep track of it all, and I'll project it all back together, and I'll make a 3D view. No one had any idea that was going to happen. Radon was a mathematician and worked on this problem because it was beautiful. And it's turned out to be phenomenally useful. Well, it turned out to be phenomenally useful 50 years after he worked on it, and now 100 years later, we can really appreciate why it was great engineering and why it was important. But at the time, no one really thought it was important outside of the mathematics community. Shouldn't matter, work on beautiful problems. So then Maxwell came along in the late 50s and worked on problems in astronomy. It turns out that a lot of the same ideas that underline Radon's work apply in astronomical imaging. And so the detection of disease in humans is intimately connected to the detection of distant galaxies. The mathematics, the science, all sort of overlaps. And so Bracewell's work on projections really fundamental to the way we think about the inverse problem for CT today. Then the guys who really got the credit, again, won a Nobel Prize for the work, were Cormack and Hunsfield. These guys worked independently. They both had this kind of intuitive idea of the back projection that I described to you, and essentially invented what we now think of as CT. It took another 15 or so years before there were commercial machines widely available, but this work took place in the 60s, and they were awarded the Nobel Prize for their efforts in the late 70s. All right, so that's CT, X-rays to CT, one kind of inverse problem. So I'd like to talk about another kind of inverse problem, and that is MRI. So most of you are probably also familiar with MRI. MRI is an interesting problem because when you start with X-rays and go to CT, you go from something which isn't an image but really still looks like something, right? An X-ray is a shadowgram. it looks pretty much, you see the skeleton, you can do things with it. As an imaging technique, measuring spin flips doesn't do much for you at all. There is no direct imaging method. So you collect data, and then you must have a computer, and you must have a solid understanding of the physics of what's going on, and then you can make images. So I like MRI for that reason. And I have a herniated disc in my back. I like MRI for that reason as well. MRI really begins with, a fundamental technology, nuclear magnetic resonance spectroscopy. And the physics that goes in is, again, Maxwell's equations. Maxwell's equations kind of goes into everything. But then, as Kent was saying, you need to have quantum mechanics. You need to understand the quantum mechanics of spin, which then, these two things together give rise to the resonant condition, the Lamer frequency in MRI. You put that together with the science of real-world measurements, statistical mechanics, and you get out things like the time constants of dephasing and relaxation, which are the things that are actually measured in MRI. Okay, so where does this begin? The fundamental discovery, again, that little triangle, the cycle, right? Turn, 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 do everything, turn. Oh, sorry. You go back to that little triangle, and the discovery here begins with a scientific question. And it's a question that I've given a talk like this to an audience that included a lot of kids, and they really like this bit because you can get them, you can actually bring in a helium and a hydrogen balloon and hold up a match to each of them. One of them explodes, one of them doesn't, and the discovery of MRI is fundamentally related to the answer to the question, why does one explode and the other one doesn't? Okay, so why would that be the case? If you look at hydrogen, hydrogen is a proton with an electron orbiting it. That electron is, as Kent pointed out, a fermion. It doesn't like to live with other fermions. So once it occupies the first lowest orbital shell of hydrogen, that shell ought to be full. Hydrogen ought to be a noble gas. It ought to be inert. It shouldn't explode. Helium has another electron, which shouldn't be able to fit in that lowest energy shell. It should sit in the next shell up, which will then be incomplete, and being the lone electron in an incomplete shell, it will have a very low dissociation energy, and you'll be able to kick it out and make a metal. It'll wander around. So helium really ought to be a metal. We go in the lab, we hold the balloons up, we hold matches up to them, and it turns out that helium does not explode and hydrogen does. And hydrogen then forms chemical bonds with oxygen and acts like it wants to have two electrons in its lowest energy shell, which is weird. It shouldn't be that way. So Pauli, Wolfgang Pauli, one of the great physicists of the 20th century, was trying to answer a version of the question, why does hydrogen explode in helium? It does not. So, blah. So the answer to this question really can be summed up as the Pauli exclusion principle, which I'll get to in a second. Well, let me do that a little bit more, which says that anytime you try to put two fermions in the same state and you permute their labels, so I've got Bob and I've got Fred, and I call them Fred and Bob, their quantum mechanical state must undergo a transformation wherein they pick up a minus sign. So you just swap two labels and they must be negative. And this simple mathematical statement has consequences that essentially are stated loosely in the modern vernacular as two particles can't exist in the same state. Two fermions can't exist in the same state. So if helium has two electrons in its lowest energy state, and they can't both live in that state, how in the heck are they both living in that energy state? Because that's what leads helium to be inert. That would imply that, in fact, the electrons in helium don't obey the Pauli exclusion principle, but in fact look like bosons. That when you swap their labels, you don't pick up a minus sign, you get the same thing back. But if electrons are fermions and the electrons around the helium are acting like bosons, then the only option is that they don't exist. And the other thing we're sure of, besides the fact that helium actually doesn't explode and hydrogen does, is that they do really exist unless you're a philosophy major. So, so the answer to this conundrum, the way out of the box, is to pull an accounting trick. You introduce a new state. You take the old state, the old electron states, and you stack them up in a vector. You say, well, here's function 1 that describes electron 1, here's wave function 2 describes electron 2, and now my real state is going to be this vector, or really it's not quite a vector, it's called a spinner. That's just a stacking of the two old results, and then I'm going to subtract from it the permutation of the labels. And this thing turns out to have all the right properties, and it predicts the correct behavior for hydrogen and helium. It also predicts this funky new thing in the world, this two-state thing, this extra quantum number, which wasn't there before. Chemistry leads you to discover new things in quantum mechanics. It turns out that these things will be known as the spin-up and spin-down states. Okay? Right around the same time, there was an experiment going on known as the Stern-Gerlach experiment, by an amazing coincidence being conducted by two guys named Stern and Gerlach. They took a bunch of silver atoms, cooked them off of the silver that was available. Sorry, this image is not the greatest, but shot them through some apertures, and then a strong magnetic field. Now, it was known that there was a certain magnetic moment associated with these. So you would expect that the magnetic field would take the beam of silver atoms coming through and just kind of pull it apart and smear it apart. And you'd get, sorry, again, contrast is a little poor here. This is the sort of thing I yell at undergraduates about. That you'd get this light blue smear over here. In fact, that's not what was observed. What was observed was that one set of the atoms went clearly up here. It didn't get pulled apart, it just went bang here. The other set of atoms went bang down here. And that's not at all what you'd expect. So it turns out, maybe I'll say a couple more things. So it turns out that the perfect marriage of these two results, helium doesn't explode, and silver atoms either go up or down when run through the Stern-Gerlach experiment. Those two things sort of came together. Stern and Gerlach had done their experiment, I believe actually a year or two before Pauli came up with this crazy two-state idea, and then they kind of found each other, and spin was discovered. So it turns out spin, that two-state system, is associated with an inherent magnetic moment. The magnetic spin is either up or down. So it's not just a two-state system, but it's a two-state system in which the up state and the down state interact differently with the applied magnetic field. They act like quantized little magnets that are either up or down. And this turns out to be immensely valuable when you have a herniated disc in your back. So you apply a magnetic field to a spin. The change in energy, whether the spin is up or down, turns out to be twice the Bohr magneton mu, which is just a measure of the magnetic moment of the spin, times the magnetic field B, or at least the magnetic field B in the direction of the spin. But of course, if you apply the magnetic field, the spins tend to polarize, and they're in the direction of the spin, or the anti-direction of the spin. If you then apply an electromagnetic field. An electromagnetic field has the very important property that it's electromagnetic, and so the magnetic part of that will interact strongly with the spin. More importantly, photons themselves carry energy that's determined by their frequency. And so you can match energies between the splitting in the spins and the energy in the photon, or you can think of it as hitting the resonant condition that gets this little magnet to flip over. In either event, with a splitting energy of 2 mu b, the resonant energy is 2b mu, could be 2 mu b, over h bar. Kent said in the previous talk, when all else fails and you know it's quantum mechanical, start throwing h bars at it. So you throw in an electromagnetic field at this energy, and it turns out that if you have protons, if you have hydrogen atoms, and you apply a couple of Tesla of magnetic field, then this frequency puts you in the radio frequency regime of the electromagnetic field. Okay, so now you can resonantly excite and flip spins with radio waves as long as you've got a whopping big magnet. So this raises an interesting possibility for imaging. I'd like you to, for a moment, imagine now that you have a one-dimensional patient. Being a physicist, all my patients are one-dimensional. So a one-dimensional patient along which we apply a gradient magnetic field. The simplest gradient magnetic field is just strong down here, weak down here, strong up here, linearly connected. And my linear patient has a bunch of protons of which it's made. And those protons now exhibit a resonant frequency that depends on the local magnetic field. So the resonant frequency down here is pretty large, and the resonant frequency up here is large, and the resonant frequency in the middle is smaller. And so if I now go in and excite with a radio frequency electromagnetic wave that's tuned to one of these resonances, I know that I'm getting a signal from the spin, say, position corresponding to the magnetic field that I'm tuned to right here. Okay? So now you take a resonance condition and turn it into a label from which you can map the density of spins in the patient. That's a little bit of an abuse of the actual idea, but it's pretty close. In reality, you kind of wait for you hit them with a pulse, and then you wait for the spins to decay, and you measure something slightly different. But this is the basic idea. So this is how you take a basic discovery in physics and then do some analysis of how that physics works and turn it into an imaging modality. MRI images. I'm running a little long. So MRI has a long connection with the University of Illinois, and most notably and quite celebrated, the 2003 Nobel in physiology and medicine went to Paul Lauterbur, who passed away a couple of years later. Paul was a giant in the field and a member of the Beckman Institute right here. I'm not going to take any more time with that. So I'd like to go on to the next thing. So the next thing is really, I'm going to be quick about this one because it's not medical or biologically related, although I will make it so in a few minutes. And that's, but it does have a U of I connection, and that's synthetic aperture radar. So radar is an echo technique. I send out a ping, ping, and I get a ping back. And depending on how long that took, I know how far away the reflector is, and that's how radar works. If you do something a little more sophisticated, though, and you go back to Maxwell's equations looks familiar, right? And you build in a reflectance model for your scene, and then you do some integral equation stuff, you get something out that relates the signal to the object here that you'd like to reconstruct. It's called the Stolt mapping. And it lets you take a whole bunch of data that are acquired in a radar machine and turn them into really intuitively obvious images that reflect real structure. All right. So just again to give you a little history and a little background, 1861, 153 years ago. States light is a disturbance of the electromagnetic field. It takes Hertz just 5 years to go from that realization to actually building the first radar. Most people don't realize Hertz built a radar in 1886. He actually had a range-finding device working. Marconi uses it to send messages in 1899, and Taylor and Young invent this, what most people now think of as stuff from old movies, but this was a radar that actually scanned out into the atmosphere, and these are cloud structures that you can see. All right, so the U of I connection comes when you try to take data that look like this and turn them into objects that look like this. This is a plane. This is actually a scale model plane in the lab. These are the radar data. How do you go from here to here? Well, you solve what's called the synthetic aperture radar problem. And that was done at the Goodyear Aviation Corporation in 1952, or at least the results were published in 1952 by Chalmers Sherwin. By Carl Wiley. Chalmers Sherwin, I've got the dates wrong. It was published in 51. A few months later, Chalmers Sherwin from the physics department here at the University of Illinois published essentially the same results. Something that both these folks have been working on for, the better part of a decade, and Wiley got there months ahead. So that's the connection between SAR and U of I. And SAR lets you take these funny-looking data sets that kind of look like this if you represent them this way, and turn them into things that look like this. Kent, you'll recognize Sandia in here, right? This is the National Mall. You can see the buildings and the Washington Monument. And these are the sorts of things that you can do with a computer and physics. Okay. So all of the three things that I just showed you have that structure, the broad intellectual structure of discovery, analysis, and innovation. But the sort of the way the work gets done, the real nitty-gritty structure, is that in all three of them, there was at some point developed a forward model that connects data, S, to an object that you'd like to reconstruct, eta, via some physics, K, right? And in all cases, there was developed a stable pseudo-inverse. Now, pseudo just means almost, sort of, almost. It's pseudo, almost. And if you'd really like to know about the mathematics of how this happened, since Professor Chiquette was advertising classes earlier, come take my class this fall. It's ECE 569. This is what we do all semester. We actually will look at all three of the problems I just discussed, plus a whole lot more. But essentially, the whole course can be captured in 2 lines. Essentially, there's some object I want to reconstruct. I know the physics connects the object back to data. If that happens in a way where I don't lose too much information, then I can get some acceptable reconstruction of the object. I never get the object back exactly, but I can get some approximation of the object that is related from the data via what's called the pseudo-inverse solution. Okay, so that's it. That's the background. That's the history. I'll give you 2 quick pieces from my own current research. Some of it's a little bit older and more mature, and some of it is literally hot off the presses from a paper that's just been accepted. And so I'll start off talking about the OCT problem, which is what I promised at the beginning. So OCT is a lot like radar. It's an echoing technology. You send in a ping, the ping comes back, you measure essentially the time of flight. That tells you the distance to the reflector. The difference is that in something like radar, you don't tend to see through the reflectors, and in OCT, you use the OCT in a context where you can often see through the reflectors and see more reflectors behind it. So what's done, and oh, by the way, light moves really fast. Okay, so if you want to image on very small scales, actually measuring the time of flight over displacements on the scale of microns is a bit difficult to do directly with a clock. It's a bit easier if you use what's called a low coherence source and an interferometer. And so in a low coherence source, the light gets sent into the sample, bounces back out, and then a reference mirror, which can be placed very, very precisely, is used to match paths between the reflection and the reference field. And you know when that happens because you see a big spike in the envelope of the interferogram that comes back. Okay? So, bad. Again, I'd yell at undergrads for this. But this is actually a little plot that has lines that come out like this, and like this, and like this, and like this. So the way OCT is done is that interferometry, that echolocation, is done with this low coherence interferometer shining a single beam into the sample. And then you get back something that looks like this, which is meant to be a series of reflections coming back from the sample. This is the envelope that sits over the top of the OCT interferogram. You then take that beam and move it 1 step to the side and do it again. And then you move that beam 1 step to the side and do it again. And then you compile the results and you wind up with an image that looks like this. This is a tadpole from my collaborator, Steve Bopart. So you can use this for all kinds of interesting things, like imaging pathological tissue. But if you're going to do medicine with this, you have to have a system that provides you with a reliable view. If you're going to look at the microstructure of tissue and make a life or death decision, you'd better be sure that your instrument isn't creating weird little artifacts in the image that you're looking at. So here's the problem with OCT, that if you go to very high resolution, the image gets messed up. So here's a view of a bunch of little particles embedded in a clear matrix. These particles are all around a micron in size. Scale bar here is 50 microns. They should all look point-like on this image. And in fact, around this section where the focus is, everything looks good. But what you see is that when you go to high resolutions, the beam you're using to probe your object defocuses rather quickly, and the stuff up here is all imaged in the defocused region. And these should look like points, and they don't. And if you're a doctor trying to diagnose titanium dioxide particles, you might think that your titanium dioxide is sick, and that would be the wrong conclusion. So here's the sort of cartoon version of the root of that problem. And that OCT, what you'd really like to have is a pencil beam that just goes in, a straight line, kind of like the X-ray transform. But what you get is, to a very good approximation, when you look at low numerical apertures, you get something that's kind of collimated over some finite distance. And that's fine, you can live with that. However, low NA means low resolution. So as you try to increase the resolution, you want to pinch down this waist of the beam. The more you pinch down that waist, the more quickly the beam then diverges. And the shorter the distance, the shorter the confocal length over which this thing looks collimated becomes. The distance over which this is collimated is also the distance over which this thing looks in focus. If you've ever just taken pictures with a regular camera and tried to do a very close-up detailed picture of a flower or something, you know that as you focus on something very close in at high resolution, everything behind it looks blurry. And that's what happens here. Okay, so same song, new tune. X-rays, MRI, SAR, we're going to do the same thing. We're going to develop a forward model. We're going to try to understand the light-sample interaction. We're going to check that, make sure it actually works. Then apply some mathematics, some analysis, and in the end, invert this and apply it to data. We're going to innovate. So here's the math. So again, Russian poetry, right? There's structure here. So here's my source for my OCT. It's at a position R0, and it comes out in what you can think of as a Gaussian beam coming through a lens right here that gets focused into the sample. Here's the mathematical statement that I have a field that comes out at position R0, propagates to a position R at a wave number k, frequency k, and that depends on some beam shape G and some spectral coefficient A, the power spectrum, square root of the power spectrum A. That incident field, that illuminating field, encounters some structure, eta, in the object down here and interacts with it. Some little inhomogeneity that then starts to ring when you hit it with this field. That inhomogeneity gives rise to a new field that propagates back. That's called G right here, and it's linear in all of this, so I get the incident field times the structure of the object times a Green's function G that propagates back to my detector. So that happens in lots of places in my sample, and so I add them up. Everywhere that the incident field encounters some structure in the object, it sends out a little point response or Green's function, and that happens everywhere in the volume, so I add them all up. And it gives me a scattered field. The scattered field then propagates back up to the thing that sent out the field, and just like antenna theory in RF, the beam shape G gets projected on the field that got propagated back and gives me a signal S. So now I have a model for my object. Here's the thing I'd like to know, eta. I'd like to measure eta. Here's the thing I can measure, S, and I somehow need to fight my way through 5 integrals, a Green's function, 2 copies of the aperture function to get back to the thing that I really wanted to measure, eta. So, yes? Yes. This is a great question. So one of the things we're building in here that I'm glossing over is the Born approximation, that this is single scattering. So it gets much more interesting when you try to deal with the unknown sample structure and multiple interactions with that. We're ignoring that entirely. It turns out that when you do OCT, you also ignore that entirely. And so it's a good starting point, but there's lots of interesting stuff you can do by trying to figure out how the sample itself affects the field that comes back out. What I'm talking about here about this thing coming back up into the aperture that generated it, this is really just meant to represent the lens and the collection aperture of the optics. Okay? And that's all kind of captured right here in this function G. Okay? Now there's a bunch of math here that you don't really need to care about except to say that you need to say something definite about what the beam really looks like and some of the parameters of your system. So you throw all of that at this problem. Don't worry about that. And then you go do a simulation. So remember the little particles I showed you? Here they are. And here they are simulated in the imaging. So the forward model actually works pretty well. So now we've got a working forward model. It's got all this ugliness in it, 5 integrals, a bunch of stuff to pull out. So you begin by taking the Fourier transform. So one of the things you can notice here is that there's a translational invariance. Whenever you have a translational invariance, take the Fourier transform. It's a smart thing to do. You then, once you've taken the Fourier transform with respect to the transverse coordinate over which the data are collected, you wind up with a 3-folded integral, and that's better than a 5-folded integral. You then go and do some math on either this term or this term on which you make asymptotic expansions of the integral. That just means we evaluate the integral for points that are either very far away from the focus or right in the focus. And in either case, there's an asymptotic regime where we can evaluate these integrals. And then we get something that looks like this. And how many integrals are there? Here. You don't see any, and that's the right answer. There are none, which is the right number of integrals to have. There are 0, because now that's the right number to have, because now I can solve this problem algebraically. And to just make it a little more readable, here's what I just derived. That the signal, S, under a Fourier transform, that's fine, it's just a rotation, is proportional to some proportionality k, a Fourier transform of the thing I wanted to find, eta. And now, the easy thing to do is you say, okay, divide S by K, Bob's your uncle, you're done. It's not quite that simple because there's noise and there's a whole bunch of other stuff. And so instead of doing that, you multiply by the conjugate and then you divide by the square and then you add something at the bottom so that the noise doesn't kill you and it makes it all stable. But it's basically dividing by K. And now you'll notice that the argument here and the argument here are different. And you need to do something called resampling. So you acquire data on one grid, and you really want to know your object on another grid in the Fourier of the object. Turns out to be a resampling problem. And remember MRI and CT, one of the details I didn't go into is that those can all be mapped onto something called the projection slice theorem, in which you resample from a polar grid onto a Cartesian grid. This problem turns out to be equivalent to a resampling from a hyperbolic grid onto a Cartesian grid, which is actually good news because it doesn't have quite the same nasty singularity at the origin. It's actually better behaved than the MRI problem and the CT problem. But the really good news is that these kind of resampling problems can be implemented really fast. And so this is where I get to say that, in fact, video games save lives, because the reason we can implement this approach, this implicit algorithm here really fast, is that we do the whole thing on GPUs and it's highly parallel, which doesn't happen without video gamers. So here are some raw data. Again, these are tiny little particles in a clear matrix. Here it is with the algorithm applied. So they should look like little points. The raw data look like this. These are really blurred out very far from the focus back here. Plane 3 is a little closer to the focus. They look a little more point-like. And when you run the algorithm, you get points, which is what they should look like. This is just rendered in 3D because it makes me happy, and it turns into that. So this solves the basic problem of the defocusing in OCT, and it means that you should not anymore worry about trading off between resolution and the distance over which you can reconstruct your image. You can have your cake and eat it too, which isn't quite true because you do pay a little bit of a signal to noise penalty. For those of you interested, we can talk about that later. But it does mean that you effectively have an infinite depth of focus at an arbitrarily high resolution. Okay, so here are, no one really cares about titanium dioxide particles. Here's breast cancer. The top are, this is histology. The top pictures are the unprocessed OCT data, and the bottom pictures are the ISM reconstructions. If you just say go, the slice A is the one that's farther away from the focus. Here, in the reconstruction, you can see these big open voids. These are lipid cells. They're healthy. They look good. Yes? Mm-hmm. Yeah.
In practice, what is the limit?
Signal to noise. There's a 1/distance fall off in signal to noise in the reconstruction. And so at some point, it looks like garbage because your signal to noise kills you. And you can't see through brick walls either, you know. So if you have a hard object, you won't see through it. But it becomes noise limited rather than, you know, fundamental physics limited. Okay? So, raw data, useless. Reconstructions, look, lipid cells. Again, lipid cells, useless. That's the story. So, Steve and I are currently busy trying to bring this to market. The thing you can do with this might not surprise you, is look at breast cancer. That's why I showed you breast cancer. And this is now a high-resolution OCT machine packaged in a fairly small handheld wand. And it's small because you no longer have to worry about refocusing through the sample. You just leave the focus fixed, and that lets you build in fixed optics and lets you build things small and compact and robust. Luke? No. The other hardware you need, in some sense, there's a hardware requirement that you require phase-stable data, which in the bad old days was a real challenge, and we had to do all kinds of funky tricks with the hardware. Now the lasers are getting fast enough that it almost comes for free. Basically, if you make a really fast measurement, your phase remains stable. Okay? So we're dealing with an A scan rate in the 50 to 100 kilohertz range. That's fast. And there you kind of get the phase stability almost for free. You have to work a little bit, but not very hard. In the bad old days, we were working at sort of the 10 kilohertz regime, and there it's a mess, and you have to have a reference surface and correct the data later. Yes? So you can look at molecules and proteins, but not individually. Yes. Yeah, and so it's OCT basically with an infinite depth of focus. And so anything you can see with OCT, you can see with this. The interesting thing is you can push OCT into a very high NA regime where you can get the resolution down to about the 1 micron scale, which isn't really, you know, it's not molecular size, but it's pretty small. You can see subcellular structure. Okay. Okay. So now, for something completely different, and I'm doing to you what Kent did too. I think I've got 2 more things left, and I'm basically out of time. Sorry. So we're going to fly through this. I've only got 1 more thing left. So the other things I work on is something called near-field optics, and I'd skip this entirely, but I think we've got near-field related folks in the field. Actually, we have student Peter So here, and Peter was a mover in the field, and so I hope you'll enjoy this. The rest of you. Anyway, near-field optics is one of my old flames. I love near-field optics, and I'm still active in it. I tried to give her up. It's a really hard field to work in, and I couldn't quite walk away. And so I'm back working on near-field optics again, and we've made some progress. But the idea with near-field optics is this. You don't like resolution limits, but you want to work at long wavelengths or low frequencies. So you have to take a probe and bring it in close to your sample and put a tiny little aperture or some tiny little metallic probe near the thing you want to measure, and measure the signal as you control the position of that probe. And you know the position of that probe. That's near-field optics in a nutshell. And it lets you go deeply sub-wavelength. So here's a nice example from the early 90s when I started working on these kinds of problems by Betzik and Troutman. Eric Betzik is one of the guys behind the storm techniques. No, he's behind Palm. Oh my goodness, he'd be very upset if I confused them, but genius guy. This is a really nice demonstration of one of the problems with near-field optics. If your probe is very, very close to the sample, you can make very highly resolved images. And so this is a 1 micron scale bar. The wavelength being used here is around 600 nanometers. So this is a little bit sub-wavelength. And this was done back at the phone company, and it says AT&T NSOM back in the days when we actually cared about funding research. They make the image over and over again, pulling the tip back a little bit from the surface at each stage. By the time you get back to this last panel, you're about half a wavelength back from the sample, and you just don't see anything really sub-wavelength. And that's the problem with near field. It's the near. So here's so what did we do? Oh, I'm getting ahead of myself. I'm running out of time too. All right, so here's a near field measurement. And never mind all of this right now, except to say that these are 2 data sets acquired from the same sample in 2 different near field measurements. The difference between them is we changed the illumination conditions. So this is bad. Your recovered structure shouldn't depend on your illumination conditions. We were also offset from the sample a little bit. So this is essentially demonstrating the problem with near field if you're not bang right on top of your sample. Okay, so this is a bunch of math that even in the context of Russian poetry is going to be a bit difficult to explain, except to say that this is the forward problem. Okay, so this is the math that describes the relationship between the thing I'm trying to measure and the data that I can measure. Okay, more of the same, but here, calculation of the pseudo-inverse. So I get down to the bottom here, I calculate this thing k plus, which is that operator that I wanted to act on my data to give me back the thing I'm trying to reconstruct. And so I do that. I take essentially the data represented by these 2 images, and I apply that pseudo-inverse operator, and I get this reconstruction, which it turns out is terrible. It doesn't work. It doesn't work really at all. And the reason it doesn't work is that I got the physics wrong. And so I like to present this example because remember the triangle. Discovery, analysis, innovation. If you blow the discovery part, you don't get to the innovation. Okay? So it turns out that you have to really take into account multiple scattering between the sample itself and the tip. And so when you were asking earlier about this interaction between the multiple times of the sample field, this is kind of what comes in here, except instead of just the field, it's this, you bring in this near field tip and it interacts with the sample and there's all this crazy stuff that goes on. But if you do it right, you get out to the end, and instead of getting this, and by the way, this is the right shape, this is the AFM of the thing we're trying to measure. Here's the reconstruction, which is actually much better than this for reasons that I don't want to go into right now. But so if you do get the discovery part right, you get to do the innovation part a little better too. So here, it turns out that this is the bit of physics we missed, summarized in just 1 term. It's an interaction of the field with the near field tip, with the sample, and with the tip again. And it turns out that besides being a nuisance in the old way we were trying to do reconstructions, it's not a bug, it's a benefit. And so what we figured out is we could take this term and use it to extract data, extract more structure from data that are acquired by scanning the tip not only over the sample, but up and down in volume above the sample. And so this is the bit that I said was going to be hot off the presses. So we did this. We got images that kind of look like those AT&T SNOM images where they're blurry and they're terrible, but some of them are good and some of them are bad. And we took all of that and turned it into a depth profiling technique. So here's a model that sort of diagrammatically shows some of the field, tip, sample, substrate interactions. The substrate is actually silicon, and this is silicon dioxide glass. Silicon has a very high, silicon has a very high index, silicon dioxide has a very low index, and we reconstructed from this model, by solving the inverse problem, both the depth of under this surface of the silicon wafer, so the depth profile, and simultaneously the index of refraction of the silicon dioxide itself, which turn out to be fairly useful things for things like nanomanufacturing. And oh, by the way, the resolution here is around 20 nanometers, and the wavelength being used is 6 microns. So more of the same, really, reconstructions of three-dimensional objects, or at least the surfaces of three-dimensional objects, and the corresponding indices of refraction, or at least the susceptibilities of the materials making up those objects. And so we can do this across wavelengths and do chemical identification and structural identification on deeply sub-wavelength scales all simultaneously. So I'd like to conclude there with what I started with, that inverse problems really let you go from a discovery of a new mechanism to make measurements to an analysis of the physics and the engineering, sometimes the chemistry of those measurements, to solve the inverse problem and create new innovations on the imaging side. Thank you for your time, and I hope you have a good lunch. So I think we have time for one or two quick questions. You went really long there. Yes, hi.
You were showing the OCT data before the ISAN application for the far objects of the blur.
Yep.
That reminds me a lot of the right half of like light sheet microscopy also falls off in contrast and loses signals.
Yep.
And I've only just recently been reading about illumination with a vessel beam to penetrate farther and get better contrast on that far side. And I wonder if there's any application to that in OCT as well.
Yeah, absolutely. The only thing that really changes, and we've written about the general case of this, that what I showed you here, kind of the math, I said I don't bother with this, built in Gaussian beams, which is essentially what you get out of a single mode fiber when you focus, right? It doesn't have to be Gaussian beams. You can run this thing through any aperture function you want, including something that generates Gaussian beams. And whereas here, you really, the goal is extended depth of field. For things like Bessel beams, the price you pay for the longer depth of field are these terrible side lobes. And so, in fact, if you get the same basic spatial bandwidth out of it, you may be able to correct the side lobes with this kind of approach.
Why were you using 6 micron light?
Because it's a spectroscopically interesting range for the kind of samples we're looking at.
Can you tell me more?
Sure. So one of the things that we're looking at is, besides what I showed you here today, is it's a little embarrassing to say because everybody's looking at it, graphene. And in the mid-far infrared, there are all kinds of interesting things that happen on the plasmonic side. And so we built a system to image those kinds of things. I don't know if that's what your appetite is. Answer the question.
So would it work with 500 nanometer light?
Oh yeah. Yeah, no, we've done it also with 500 nanometer light. Yeah. I just like to show this because it's 500-fold reduction below Rayleigh criteria resolution, right? And so you go, oh look, I beat the resolution limit by a factor of 500. It's a bit of a dodge because really, once you're doing near-field optics, the only thing that limits resolution is the probe sharpness. And so if you do it at 500 nanometers, you also get 20 nanometer resolution. And if you do it at 10 microns, you get 20 nanometer resolution. So, yeah. But it looks more impressive when you do it that way. It's coming out in, where was that? I think that was just accepted at ACS now. So it'll be on ACS now shortly. Any other questions? Okay, thank you very much.